let's look at how we can apply L'Hopital's rule when we're given this indeterminate form. This does not meet the conditions of applying L'Hopital's rule, but we can again manipulate this legally, mathematically, algebraically into the form 0 over 0 or infinity over infinity, and then apply it. So let's try this limit, see what we can do here. And when we look at this, we've got 1 divided by 0, which is basically an infinity, minus 1 over e to the 0 is a 1 minus 1, 1 over 0 is another infinity. So basically have infinity minus infinity. So we're looking at this indeterminate form. This does not meet the conditions of applying L'Hopital's rule. So because in order to apply it, you have to have a 0 over a 0 or an infinity over an infinity, that division of indeterminate form. So what can we do here? We're going to try to rewrite this into that sort of quotient. When you have a sum, finding a common denominator, that's always a good thing to try and see what happens. So let's see that. The lowest common denominator here would be x times e to the x minus 1. So if I got this lowest common denominator, I would multiply this x times e to the x minus 1 in the denominator and the numerator. So my numerator becomes e to the x minus 1 for this fraction, minus, if I have e to the x minus 1 and I have this new denominator, I multiply the numerator and the denominator by x. So this becomes this times x, this times x. This is my new common denominator, one fraction. The limit as x goes to 0 plus. I have done nothing. I've not applied a rule. I've just found a common denominator and combined these fractions. Okay, let's see what this gives us. If we plug in 0, we get e to the 0, which is a 1, minus a 1. We plug in 0 for x, minus 0. Okay. Down here we have 0 times e to the 0 is 1 minus 1. We're looking at a 1 minus 1, which is a 0 minus 0, a 0. 0 times 0 is a 0. We've got this indeterminate form, which means now that we made it look like this, we're allowed to use L'Hopital's rule. So now we will apply L'Hopital's rule. And once we do that, this is the limit as x approaches 0 from the right. So it's a one-sided limit, but we already discussed it's okay. L'Hopital's works for one-sided limits too. The derivative of this numerator over the derivative of the denominator. So the derivative of e to the x minus 1 is e to the x plus a 0 plus the derivative of negative x, which is negative 1. This is what I get when I take the derivative of this top function over the derivative of the bottom function. Well, this is a product, so it's first times the derivative of e to the x minus 1, which is just e to the x, plus second, e to the x minus 1 times the derivative of the first, which is just a 1. Let's see, what do we get when we put in 0? This gives us e to the 0, which is a 1, minus 1, over 0 times e to the 1, e to the 0, which is a 1, plus e to the 0, which is a 1, minus 1 times 1. We get 0 over 0 plus 0. We get another 0 over 0. When this happens, and it does, you can apply and should apply L'Hopital's rule again. So, because it still meets the conditions. Let's go around again. So now, let me just clean this up a little bit. Let me simplify this. So it meets the conditions to apply it again. So let's apply L'Hopital's rule again. Apply again. Let's see. What's going to happen here? This is just this is the limit as x goes to 0 from the right of e to the x minus 1 over x e to the x plus e to the x minus 1. Okay, this is what I'm about to do. Take the derivative of the numerator, which is just going to be e to the x over the derivative of the denominator. Okay, product rule. First times the derivative of the second plus second times derivative of the first, which is 1, plus the derivative of e to the x, which is just e to the x, plus 0. Okay, now when we plug in 0, what do we get? We get e to the 0, which is a 1, over 0 times 1, plus e to the 0, which is a 1, plus e to the 0, which is a 1. We get 1 over 2. That is what the limit of this ended up being. We had to apply L'Hopital's rule 2 times, and sometimes you do that. That's okay. Let's look at this guy. What's going to happen here? Remember your unit circle. Remember that cosecant is 1 over the sine. Remember that cotangent is cosine over the sine. That's what cotangent is. Okay, so if we're looking at 0, which is this angle right here, and this is the point 1, 0, 1 over 0 is an infinity. Cotangent would be the cosine 1 divided by the sine, which is 0, 1 divided by 0, which is another infinity. We're looking at this same indeterminate form. We cannot apply L'Hopital's rule given this situation. So let's see what we can do with it. Let's rewrite these into their basic functions. This is equal to the limit as x goes to 0 of 1 over the sine of x minus the cosine of x over the sine of x. And this is a, already has a common denominator, so let's just write it as one function. So this is equal to the limit as x goes to 0 of 1 minus the cosine of x over the sine of x. Okay, let's throw in the direct substitution. 1 minus the cosine of 0 is 1 minus 1. Okay, over the sine of 0 is 0. We're looking at a 0 over 0. We're looking at the indeterminate form 0 over 0, so we can use L'Hopital's rule. So let's do it. Excuse me. Excuse me. Okay, so we're going to apply L'Hopital's rule. So once we do that to this, it met the conditions. This is the limit as x goes to 0. Derivative of negative cosine is going to be a negative sine. Derivative of sine is cosine. This negative times negative is a positive. The sine of 0 is 0. The cosine of 0 is 1. This is what the limit is of that guy. So that's how you can handle differences, infinity minus infinity. Now, we're going to look at what to do when we have those crazy indeterminate forms that are powers. So let's see what happens there. You have to handle these a little bit differently, but you guys have the skills to do that, so it shouldn't be a problem for you guys. So we looked at the differences. Now let's look at the powers. Okay, here we go. Okay, so we can have indeterminate forms that involve powers that look like this. We could have a 0 to the 0. We could have this. We could have infinity to the 0. We could have 1 to infinity. These are all indeterminate powers that you're not sure who's going to win, the F or the G, who's going to overpower who. So, because anything to the 0 power is 1, but 0 times itself is 0. What are these? We can't really tell. So when we're given these indeterminate forms, we have a way we can work it into using L'Hopital's rule, and this is basically how we do it. Let's look at a couple of these. This is number 8, I think, on your sheet, and we have the limit as x goes to 0 from the right of x times the square root of x. Okay, and then number 9, we're going to do this one. The limit as x goes to 1 from the right of x raised to the 1 over 1 minus x. Okay, so first, use direct substitution, see what happens. So if you use direct substitution here, we basically have a 0 raised to the 0. We're looking at this indeterminate form. Okay, so we can do some manipulation and get this to work out and apply L'Hopital's rule. I'll have to show you how to do that, and you'll know how to do that soon. What about this? When it's 1, we have a 1 raised to the 1 over 1 minus 0. 1 minus 1, 1 over 0 is infinity. We're looking at this one in this case. So if I did an example where we had this, you could also apply this the same way. Okay, this is how you begin this process. You say, this is a function. Let's think of x to the x as a function. Y is x raised to the square root of x. And so what we're going to do is what we have done before, and it's very helpful sometimes to introduce a log when you have a power, because we get to use the properties of logarithm in that power rule. So let's do that here. Let's take the natural log of both sides. So the natural log of y is equal to the natural log of x to the square root of x. And so what we're going to do here is use the power rule, where we get to throw the power in front. So this is the natural log of y is the square root of x times the natural log of x. Okay, so that is good. Now, what can we do with this is, once we get it to that state, we will go ahead and apply the limit back in. So let's look at with the limit as x goes to, the limit as x goes to 0 from the right of the natural log of y is the limit as x goes to 0 from the right of the square root of x times the natural log of x. So let's concentrate on this guy. If we use direct substitution, this would be a 0 times infinity, as we saw earlier. Okay, this is an indeterminate form, but it's a product. We need to rewrite this into a quotient. So let's make this look like a quotient. The limit as x goes to 0 from the right of the natural log of x over 1 over the square root of x. What does that give us? And I did that same little trick by dividing the numerator and the denominator by 1 over the square root of x. This gives us negative infinity over 1 over 0 is an infinity. We get an infinity over infinity type indeterminate form, which says that we are allowed to use L'Hopital's rule. Okay, so now let's apply L'Hopital's. Okay, what do we get here? This is equal to the limit as x goes to 0 from the right of the derivative of natural log of x, which is 1 over x, over the derivative of, this is basically 1 over square root of x is really x to the negative 1/2. So if I take this guy's derivative, it's negative 1/2, woohoo, x to the negative 3/2. Okay, so let's apply this. Let's see, this is really the limit as x goes to 0 from the right of 1 over x, which is x to the negative 1 over negative 1/2 x to the negative 3/2. Let's raise this x to the negative 3/2 up, and when you cross the fraction bar, it gives it a positive. So this is going to be 3/2 minus 1, or x to the 1/2. Okay, this is, we could say, this is the square root of x, or the square root of 0 divided by negative 1/2 is 0. That is what we get right there. Okay, what in the world is this? What did we just find? We found the limit as x goes to 0 of the natural log of y. This is what this equals to. This, after we use L'Hopital's rule, equals to this. Okay, we are not done. What we were asked to find was the limit as this goes to this, which I said this is y, right? So really we want the limit as x goes to 0 from the right of y, not the natural log of y. We are going to use this fact right here. Use the fact that y is equal to e to the natural log of y. What we want is the limit, ready? We want the limit as x goes to 0 from the right of y. So this is the limit as x goes to 0 from the right of e to the natural log of y, which we just found out that that is 0. So this is basically e to the 0, because the limit of the natural log of y is 0, and so this is what the limit is. It's 1. All right, we're going to see that one more time in number 9. Over number 9, this is what we do. We already did the direct substitution. We found out that we got this indeterminate form in the power. So what that means is, let's proceed. let's see, let's let y equal to x to the 1 over 1 minus x. Let us take the log of both sides. So the natural log of y is the natural log of x to the 1 over 1 minus x. So the natural log of y, we'll use the power rule, is 1 over 1 minus x times the natural log of x. Now, let's introduce the limit back in. So let's take the limit. The limit as x approaches 1 from the right of the natural log of y is the limit as x approaches 1 from the right of 1 over 1 minus x times the natural log of x. And when we put that in there, we get 1 divided by 0, which is infinity. The natural log of 1 is 0. So we get this indeterminate form. We cannot quite apply L'Hopital rule directly. We have to rewrite it into a quotient. So let's do that. This is equal to the limit as x approaches 1 from the right of 1. Oh, we could just do this. We could just multiply this into the natural log of x over 1 minus x. Let's look at this. Natural log of 1 is 0. 1 minus 1 is 0. Just by multiplying that together, we got the form that we needed in order to apply L'Hopital. So let's do that. All right, so when we apply, now we can apply L'Hopital's rule, and it goes like this. The limit as x approaches 1 from the right of the natural log of x is equal to the determinant of the numerator, 1 over x, over the determinant of the denominator, negative 1. Well, this is we can use direct substitution. 1 over 1 is 1 times the negative 1 is a negative 1. All right, we are ready. Again, we're going to use the fact that y is equal to e to the natural log of y. So what we really are after is the limit as x goes to 1 from the right of y. And what we have, this is equal to, hang on just a second, the limit as x goes to 1 from the right of e to the natural log of y. So this is equal to, we know that the limit as x goes to 1 of the natural log of y, right? This ended up being this. So this is basically e to the negative 1, or 1 over e is what the limit's going to be. So that's how we can use it when we have an indeterminate form that is of a power nature.